Quick summary here. Problem 4, we draw the displacement vectors. They don't have to be drawn head to tail. We have two separate displacement vectors. You can put one in the next room and one here. I've just separated them excuse me, by short distance. We have three situations, one of which lacks the frictional force, one of which the frictional force is smaller than what we have here, and the third situation where the frictional force is larger. And that's the main difference between the situations. Now, all you were asked to sketch was the weight vector and the displacement vector. Okay, the weight vector and the displacement vectors. Okay, the weight vector is the same both times. Displacement vectors are going to be different. But this is what the pictures are going to look like. Now, some of you went ahead and put normal forces and so forth in there, and that's okay, but the normal force has no contribution to the motion of the ball. Once you know what the frictional force is, and this is a small angle approximation where the normal force is going to be pretty much equal in magnitude to the weight, it's not really necessary to consider the normal force, but it also is probably a good idea to include it here, because you want to remind yourself that if we don't have the small angle approximation, you do need that normal force. Now, on the next problem, where the ball starts from rest and ends up 2 centimeters lower, of course, we can do this using MGY, but that's not what we want to do. We want to do a little more than than just use a formula to do this. We want to build insight, and the insight is built by understanding how the weight vector and the displacement vector articulate in order to give you the result. So briefly, we want to find the change of potential energy. We draw the weight vector along with delta x1, the displacement down this incline, and then the weight vector with delta x2, the displacement up this incline. And we project the delta x1 and the delta x2 onto the weight vector, and we get a delta y vector, which is in the downward direction here, and a delta y vector, which is in the upward direction here. And when we add those delta y vectors to calculate the work done, when we calculate the work done by gravity, the work done here is going to be positive. It's going to equal the magnitude of the weight vector times the magnitude of the delta y1 vector. I didn't put absolute values around the weight vector before, so it should be clear what that meant, but just to be consistent, I'll go ahead and do that throughout here. We get the work done by gravity on the ball on the first incline, the work done on the second incline. On the second incline, the work is negative because the vectors are in opposite directions. And then we add those up. This is going to be positive, this is going to be negative. We factor out the weight, and we find that we're just multiplying the weight vector by the difference in the two positions. The change in the y1 position, magnitude of that change minus the magnitude of that change. That's just 2 centimeters. It gives us 4 newtons times 2 centimeters, 0.08 joules. And I'll remind us that's not 8 joules as you might get if you leave off the units, and as some people did get. The change of potential energy, therefore, being equal and opposite to the work done by gravity, is negative 0.08 joules. If there's, well, that's sufficient to this particular board. When the ball goes down one incline, up another, and back up another to the original point without losing any energy to friction, or actually it doesn't matter whether it loses energy to friction or not, if it manages to get back up here, we want to analyze the change in potential energy. And of course you can use MGY. Y is the same at the start as at the end, so there's no change. But we want to see how that works out. So we draw the displacement vectors and the weight vectors, project the displacement vectors onto the weight vectors. We get a delta y1, a delta y2, and a delta y3 for the 3 different phases of motion. And we easily argue that the downward displacement here is equal and opposite to the upward displacement, the total upward displacement of these two. we do that with symbols, and we conclude that the work done by gravity is zero. It follows that the change of potential energy is equal and opposite to the work done by gravity, which is zero. So the change of potential energy is zero around this closed path. This argument can be extended to any path, and we saw that in previous videos. We're just trying to reinforce it here. So this is the analysis that we would have hoped for on this problem. I don't remember which problem this is. Just doing a quick summary here. We have that in detail on the other videos. For the Atwood machine, we sketched the forces, and then we sketched each force with the displacement of the particular weight. This 5 Newton weight descends 0.6 meters, so that the 4 Newton weight has to ascend 6 meters, and we get the change of potential energy here, which is going to be -3 joules, very easily calculated, and the change of potential energy here, which is going to be +2.4 joules, again, very easily calculated. If you want further discussion, you check the original video. Okay. The total potential energy change is the sum of the two potential energy changes, and that's clearly the sum of these. It's going to give you -0.6 joules. The change in kinetic plus a change in potential energy is going to equal the work done by the non-conservative force. Under the assumption of the problem, that work is zero, no friction involved, so the change in kinetic energy is 0.6 joules. Now, continuing the same situation and summarizing the results from before, the potential energy change of -0.6 joules. If there's no friction, then the work done on the system by non-conservative forces is zero, so that the change in potential plus change in kinetic being equal to that is equal to zero, meaning that the change in kinetic energy is equal and opposite to the change in potential energy. Now, if there's friction, which is the situation that we're analyzing here, that friction is 0.06 times the total weight. Well, the total weight is 9 newtons, assuming that the pulley and the cord are of insignificant weight. We multiply that out and we find that there's a 0.54 newton frictional force opposing the motion, so that the work done by non-conservative forces on the system, friction is opposing motion, so we take the negative of the product of the magnitude of the friction and the displacement, and we get the work done by friction, which is -0.3 joules. Okay, now we got -0.324, but that's a ridiculous number, significant figures given this accuracy of the other calculations. We round that off to -0.3 joules. And we add that's going to be the work done by non-conservative forces, which means then that the change in potential plus change in kinetic energies is going to be equal to the work done on the system by non-conservative forces, the -0.3 joules. And we can use that up here to calculate the change in potential energy, and it's a very simple calculation. We know the potential energy change. That is not affected at all by how much friction there is or what else is going on. The change in potential energy depends only on the initial and final positions, and that's as it was originally, -0.6 joules. We know the work done by non-conservative forces on the system, so we very easily calculate the change in kinetic energy, which is going to be, well, we're going to add the 0.6 joules to both sides. We're going to get plus 0.3 joules, and let me kind of put an emphasis on that, emphasizing that that's positive. Now, the next situation that we dealt with was the pendulum. Okay, pendulum of length 120 centimeters, pulled back 20 centimeters, is going to be about 2 centimeters higher than at its equilibrium position. The vector from equilibrium to the center of the, from the equilibrium position to the pullback position, therefore, looks like this. And that vector is just, that vector doesn't care that the pendulum is going on a curved path. It just cares about where it starts and where it ends. That's how we're going to calculate the change in potential energy. So we go down here, we calculate the delta S, the displacement, of the pendulum. That's going to be about 20 centimeters this way, a little less. Pythagorean theorem is going to give you a small difference there, 0.5%, I think. The J component being 2 centimeters up, the 2 centimeters being the difference between the 118 and 120 centimeters. It should be obvious that if the pendulum is back at equilibrium, then the distance from here to here is going to be 120 centimeters, where the distance from here to here is only 118 centimeters, making this displacement 2 centimeters upward. Now, we went ahead and did the vector form of the delta S, and we can do the vector form of the delta Y, which is 2 centimeters times J. We do the dot product then of the negative 12 newtons times J plus the 2 centimeters times J, and we get negative 0.24 joules. Now there's some error in this because we rounded this off to the nearest whole number, and there's actually, I think, 118.3 or 118.4 centimeters. That causes some error here. And the actual result is more like 0.20 joules. Okay. Note that we would have gotten the same thing had we multiplied the negative 12 newtons times J, which is the gravitational force vector. If we had taken the dot product of that gravitational force vector with the full delta S vector, there's no I component to the gravitational weight, to the weight vector, the gravitational force vector. So you're going to get 0 out of the 20 centimeters, and that justifies using only the 2 centimeters times J in this calculation, but it works out either way. Work done by gravity on the system is negative 0.24 joules, so the change in potential energy excuse me, is plus 0.24 joules, more accurately plus 0.20 joules. So potential energy change from here to here is plus 0.24 joules. If the pendulum swings back, you're going to get negative 0.24 joules because the position just goes in the opposite direction from here to here. Work done by non-conservative force on the system. If that work is negative 0.01 joules, and this is one of the conditions in the problem, we get that the kinetic energy change is equal to the potential energy change plus the delta W non-conservative, etc. And you can work out the details of that. You get 0.14 joules, which you set equal to the 1/2 mvf squared. If you don't have the negative 0.1 joule of work done by the air resistance, if you have 0 non-conservative work done by the non-conservative force, then you're going to get the full 0.24 joules, which is actually 0.20 joules if you do this to two significant figures. I'm going to mention finally that there is no place in any of these calculations for analysis using the equations of uniformly accelerated motion. It would be particularly inappropriate here because the acceleration is not uniform. The force, the net force on the pendulum changes with position. So no use of the equations of uniformly accelerated motion is appropriate to the analysis of a pendulum. The energy analysis is. Now you could use the equations of uniformly accelerated motion with any of the other situations. If you had the details, the Atwood situation would be fairly straightforward. But it's unnecessary. We want to get in the habit of thinking in terms of energy. We already know that we can think in terms of uniformly accelerated motion, and we know that we can analyze it. We don't want to fall back on that when we're trying to learn to use energy conservation. The fact that delta W NC on is delta PE plus delta KE.